Welcome. I'm going to do an inclined plane sample problem for you. And then you get to do a whole bunch of multiple guess ones on your homework tonight. Okay, so I'm going to start with the letter green. All right, and we're going to use these same set of rules. Those rules are posted on the general review sheet. They're at the top of the regular free body diagram on the flats problem. All right. And notice that I've highlighted or I've bolded a couple of statements in each step to help you remember them. So the first one is a free body diagram. So you draw it free from its surroundings, but for inclines, I at least draw the incline. Okay, I like to use a box. Okay, and then we're going to label all the forces on the box. Let's see if I can find my labeling sheet. Okay, so let's examine which forces might be acting on this thing. And this is a 260 kilogram safe that is sliding down a ramp. All right, they talk about the coefficient of friction and they want to know about its acceleration. All right, so does gravity apply? Yep, always does. Doesn't always matter if you're looking at the bird's eye view like we were with the can opener, but it's always applying. Okay, next, is there a surface supporting it? Yes. So we're going to do, remember normal means perpendicular, so we're going to do a normal force perpendicular to the surface. Okay. So this is this. So this is perpendicular to the surface, but since my box is also, I got parallel sides, it's perpendicular to the box. Okay. Let's see. Is there an applied force? Well, they don't talk about anyone pushing the slide or the safe, so I'm going to assume a no. Okay. There's no strings involved. Or any of the other obscure forces that we've talked about. So how about friction? And they mention friction here. As I say, use friction if it's needed or to explain why something's slowing down, or if they mention it in the problem. All right, and so it'll always be parallel to the surfaces and contact opposite motion. So since the safe is sliding down, I'm going to make a little velocity vector way over here to remind me of the direction. Remember, we only put force vectors on the free body diagram. Okay. Since it's moving this way, the friction will be parallel to the surfaces in contact, but up. And that's it. That's all the forces that we have. Okay. So we're going to do our next step, and I'm going to do that in turquoise. And the reason we do this as filling in data as a separate step is to remind you, you've got to name your forces, because if we ask you to make formulas, you have to have forces to put in the formulas. And so it's important that you don't just put in the data. Okay. So we now know that the angle is 30 degrees. We know that the mass of the safe is 260 kilograms. And we know that the coefficient of friction is 0.3. Remember, there are coefficients of friction on your reference tables. In a Regents question, they'll often remind you to use them. But here's another way to know. If they're very specific about what the materials are, like rubber on dry concrete, right? Wood on wood, Teflon on Teflon, it's a hint to you that you will probably be using these, right? And remember, kinetic is when the surfaces are moving in relationship to each other, and static is the maximum static force of, or static coefficient of friction applies when something just starts to move and slips. You need to overcome this static friction. Okay. I think that's all of our data, so we can move on to a new color, and I'm going to use orange. And this is the one that reminds you mass is not weight. So in most problems, they will give you the mass and you'll need to calculate the weight. Or they might give you the weight. Watch out for that. If they tell you if it weighs something in newtons, don't go throwing it into this formula to find the weight again. All right. If they give you the mass, use this formula to find the weight. If they give you the weight, you might need this formula to find the mass. If it's accelerating, you'll probably need the mass. Okay. So remember, this formula is also on your reference tables about midway down, and it's written in a funny way, right? Okay, so just like F net equals MA is written this way, F sub G equals MG is written this way. Okay, so let's go ahead and calculate that. So F sub G equals 260 kilograms times negative 9.81. Now I said negative, but actually this is one of the times we don't want to put the negative in, because down is actually a diagonal and we're shifting our perspective And the only useful place to talk about negatives is if they're on the axis. The weight is not on the axis, so I'm not going to call it negative. All right, let's actually calculate this. Okay, and this is has a weight of 2,550.6 newtons. I'm going to circle that because it's so I can find it later. Okay, next is components. Now, in the first problem that I did this way, there weren't any components, right? But this is a little bit in inclines. There will always be components, and they will always be named the same thing. Because remember, the weight does two things. It pushes the safe into the incline, which causes it to gain traction, which is like friction. All right, and then the weight also tends to make it want to move down the hill, and that is the force parallel. In another video, I've given you how to find the formulas for this, but a couple of things to remember. This angle will always be the same as this angle because they're similar triangles. Okay, you can always work it out with right angle trig, but here's my silly mnemonic. Force perpendicular goes with cosine. Okay, so these come from the weight. So force perpendicular is F sub g times the cosine of theta, and force parallel is F sub g times the sine of theta. Okay, we can work this out because opposite goes with sine, which is why the parallel is sine, and adjacent goes with cosine, but I'm not going to derive these formulas now. I do want to warn you, they're not in your reference tables, unlike, I moved down and you couldn't see what I was doing, sorry, before. So we have the cat to complicate things. Dude, no. Okay, so where are we at? Okay, so we've got the formulas for the components. These are things you need to memorize. And again, my silly mnemonic is perpendicular goes with cosine. And if you hack and spit it enough, you might remember. Okay, so I'm going to put these in. So the force perpendicular equals the weight, which was 2,550.6 newtons, times the cosine of 30 degrees. And force parallel is equal to that same giant weight times the sine of 30 degrees. Okay, now make sure you're in radians, or I mean not in radians, that you're in degrees, and go ahead and multiply these. All right, so I'm going to pause that while I do these calculations. Okay, all right, so I went ahead and threw these in my calculator and I calculated them. We are now done with the components. Okay, now we are going to use our free body diagrams. This is the step that people tend to forget. So remember, if you're stuck on these problems, you're probably stuck on step 5 where you're writing specific forms of F net equals MA. This is the whole point of this carefully drawn picture, is to write specific forms of F net equals MA. I'm going to do this in orange, I guess. Or I did orange there. So I guess I'll do this in red. I'm trying to keep the colors the same, but I see that I didn't even do that. Ooh, I can't do it in red because red decided to go out. All right. Okay, I'm going to do pink. So looking at my picture, remember we are now shifting our axis to this way. I like to make my friction negative. So even though I drew it to the right, I'm going to make this direction negative, this positive. I like to make normal positive and perpendicular negative because that tends to always be downish. Okay, so looking at my picture, I'm writing specific forms of F net equals MA for two directions, the perpendicular direction and the parallel direction. Sorry, I'm running out of room here. I'm just going to move on. All right, okay. Equal F net parallel, sorry, equals MA parallel. So looking at my picture, in the parallel direction, I have two forces. I have force friction, and way down here, I have force parallel. It is still, remember, I could draw it here or here. It doesn't really matter. You can always move a vector in space. Equals MA parallel. And it says it's accelerating, so I'm going to leave this formula alone. Okay, in the perpendicular direction, I have two forces. I have the normal force and the perpendicular, and they both add up to MA perpendicular. things don't ever accelerate this direction. We're not having slaves bouncing down, right? Okay, that's beyond the scope of this course. So these will always be the same, assuming there's not some third force in there, like someone pushing, but again, beyond the scope of this course. So here's a hint. The normal should be the same size as the perpendicular because, hint, hint, normal means perpendicular. Okay, these will always be balanced. And since the perpendicular is this, now the way I drew this, my picture is always the ultimate decision on signs. So now I'm going to correct my sign here and say, this is actually a negative sign because it's going this way. And this parallel is a positive. Okay. All right. So let's see. We can actually plug and chug here and actually find out that force normal. Oh no, we're not plugging and chugging yet. That's another step. Done. Finally, I'm going to actually try to solve this, and I'm going to do that in black. Okay. We're trying to find the acceleration. That is our unknown. Okay. But before we can do that, we have to generate several formulas, which is why this preamble works. And we're always working to find 3 formulas. All right. One for the perpendicular direction, one for the parallel direction. On the flats, these would be x and y. And the third one is FF equals mu Fn, and that's that formula that combines friction, the normal force, and the mu. Okay, so the way these problems often go is you need a formula for the perpendicular direction, which we came up here, okay? A formula for the parallel direction, which we came up for here, and this from our reference tables. And then we can plug in and find stuff. Now, before we can find the force of friction, we need to find the force normal. So that is just balanced with the force perpendicular. So that's going to be 2208.9. All right. And then I can do, so I'm going to do that first. The second thing I can do is I can use FF equals, I'm going to try to get this a little bit more contrast there, mu Fn, okay, to find force friction. So FF equals, then the mu was 0.3, that was given, and the normal force we found out just a minute was 2208.9 newtons. Now, another thing that makes these problems hard is that this will never give you the correct sign of the norm of the friction force, but I made it negative, so I'm going to expect this to be negative. Okay, but normal forces tend to be positive, and mu doesn't have a sign, so you need to put the negative in yourself. Check signs with free body diagram. Your free body diagram is the ultimate authority on whether things should be positive or negative. All right, I'm going to do the math there. I get that the friction is negative, because I drew it negative in my picture, 663 newtons. And then third, finally, I can then come along and find my acceleration. So I have a negative 663 newtons. My force parallel that I figured out up here was a 1275.3. And let's look at our picture. The force parallel makes it want to slide down the hill. I said down the hill was positive. So that's positive. Equals the mass, which they gave us was 260 kilograms. So I'm running out of room here, times A. All right, so let's do the math here. When I subtract these, I get that this is 612.6. I'm dropping units, equals 260A. And I get that A is 2.356. All right, I'm going to round that to 2.36. And it's going down the ramp. And I know that because it came out positive. And I labeled this positive. Whew! Okay, let's sum up what we did here because this was a lot. There's the final answer. And I'll throw the key on here. So, we did a free body diagram. Okay, let's zoom out. We're running out of time here. Okay, we got a free body diagram. Okay, all right. And we labeled all the forces and gave them names. There were 3 in this case. We filled in the data. We did masses, not weight, and we used the mass to figure out the weight. We calculated the components and drew them in of the perpendicular and parallel signs, components of the weight. And then we wrote specific forms of F net equals ma to come with our 2 force balancing equations and then use that in combination with FF equals mu Fn to find our final answer. I know this is a ton of work. The good news is that the inclined plane problems on the homework are much simpler than this, but this is